So we're going to move into the Jurassic. How do I advance this? There we go. So today, first I'm going to talk about the purpose of this study, some of the applications. I'm going to go over the areas I studied, and then I'm going to kind of compare things to Mars. So I'm looking at rocks, Jurassic Age rocks on the Colorado Plateau as an analog for Mars sedimentary rocks at Gale Crater. Okay, I'm going to go through some data, hopefully not too much. SEM is just pictures, photography is pictures, so it won't be too data heavy, and so hopefully I don't lose the crowd here. So the purpose of this was to look at how microbial fossils are preserved over geologic time. And that's a question that really hasn't been answered. And to do this, I'm going to look at modern microbial mats that have ancient terraces, so 100,000-year-old terraces from the same system. And then I'm going to look at Jurassic rocks and compare these to see, one, how they're changing, and then two, what kinds of chemical and mineralogical signatures are persisting over geologic time. So you might say this is these rocks that I showed a picture of last night. They're from an alkaline saline lake, and you might say, are you comparing apples and oranges here? And not really. They both have abundant biotic features. They're both alkaline saline groundwater-fed systems, so there are some similarities. Okay. So I'm using this as an analog to the rocks at Gale Crater, which are very similar. It's been suggested that these are lacustrine in origin or were deposited in a lake system. Is this too loud? It seems really loud. Okay.
It's louder up here, actually, than back there.
Oh, okay. So anyway, the rocks at Gale Crater were possibly deposited in a lake system, similar to the lake system of the Brushy Basin Formation. They're iron and clay-rich sediments. We've heard a lot about clays. And this has application for obviously looking for biosignatures in these rocks at Gale Crater, but also for terrestrial origin of life studies, because we have heard already today that there's still some question on how to really pin down what an actual biosignature is. So, the other big thing is just understanding the basic sedimentology of Gale Crater. Like, how did these rocks form, and what kinds of environments were they formed in, and what is the history of the rocks so diagenesis is a word that I will use. Diagenesis basically means the process by which sediments become sedimentary rocks. So sediments are deposited, they get buried, water and sometimes on Earth, biota begin to interact, and they become sedimentary rocks. So that's all I mean when I say diagenesis, but that's a very big process that we need to better understand for Gale Crater. All right, so here's my cold spring system. It's in 10-mile GRABEN, which is in southern Utah in the United States. It's a cold spring system. It's got CO2 and hydrocarbon. It's been in existence for at least 400,000 years. There are abundant tufa terraces that very conveniently somebody else went out and dated, so I know exactly how old these terraces are. So it's been in existence for 400,000 years. I selected a 100,000-year-old tufa terrace to study, as well as modern springs. And these are my daughters, and today is their 15th birthday, and they're watching, so I have to say happy birthday, Lillian and Alexis. Want to hear your birth story? Okay. All right. And so then the Brushy Basin member of the Morrison Formation, those are the Jurassic rocks I'm looking at. And these were deposited, as I've said, in an alkaline saline groundwater-fed system that's centered on the Four Corners region of the Colorado Plateau. So here's Colorado, New Mexico, Arizona, and Utah. And it's been named in the literature Lake Tudichi, which is a Navajo word meaning bitter water, because the water must have been quite bitter. And we won't go into it, but there are these clay mineral zones. So I'm not going to go into depth about the clay mineralogy. There's also abundant biotic influence in this system, which I'm not going to talk about too much either. So here's a comparison of the lithofacies. So lithofacies is just a fancy word that means rock type. And so we have basically three main rock types. There's a siltstone, claystone, and these are both on Mars and in the brushy basin. So there's a siltstone, claystone facies that can be laminated, which typically means it's deposited in standing water. In Colorado, it's bioturbated, and the bedding can be completely destroyed and massive, and that's due to bioturbation. There's also a massive facies on Mars, which may not be bioturbated. You can get massive facies other ways. And then, as I mentioned last night in my presentation, there is a siltstone, claystone facies that is vuggy. So vug is a word that just means void space. And in Colorado, this is interpreted as a charophyte or a charophytic texture, which a charophyte is an algal mat, and it leaves this kind of vuggy texture in the rocks. There are sandstone facies that exhibit cross-bedding, a little small-scale cross-bedding here and there on Mars. It can be bioturbated as well in Utah or in Colorado. And these are lenticular sandstones, which suggest a fluvial, river system. So these are deposited in a river. Conglomerates as well exhibit imbrication, which means they're tilted in the direction of current, which suggests also that they were deposited in a river. So, which is not inconsistent with a lake. So you're thinking, you said lake, now you're talking about a river. Well, if you've got a lake system that's periodically desiccating and you've got rivers feeding it during flood times, think Sahara, Serengeti in Africa, or in Western Australia, the acid saline lakes and things, that you have periodic floods that come in and deposit fluvial sediments, and then you have other times where lake is the lake water is deeper and standing. Okay, so as I said, in the brushy basin member, there's abundant macroscopic biotic influence. Okay, as I've talked about the vugs, the charophytic texture. These are reduction halos around root traces. So very often you get paleosols, which are fossil soils, and you have evidence of roots and burrows in those. And the organic matter degrades and creates these reduction halos. This is a highly burrowed rock here, and this is a dinosaur femur. And as I said last night, I'm not suggesting there are dinosaurs on Mars, or were dinosaurs on Mars. But we did have them here in the Jurassic, and we do find evidence of that. So for this study, I used criteria for biogenicity from Sherry CADY, 2001, and just to have some sort of starting point. Okay. So to prove biogenicity, it has to be in a thin section. So it has to be, you have to show that it's actually not contamination, it's actually in the rock. It has to be a sedimentary or low-grade metamorphic rock, because like we've discussed, I mean, if it's in a lava, it's, unless it's not syngenetic, lava burns it up, okay? It needs to be the same size as life as we know it. It needs to have kerogen. It needs to be with others of similar morphology, so it can't be, it can't just be one isolated feature. It has to be living in a community. it needs to be hollow and have cellular complexity. And then she set up this kind of criteria. So if it meets 1 to 4 of these, it's a pseudofossil. 1 to 5, it's possible, and 1 to 7, it's probable. Okay. Oh my God. All right, so I'm going to go fast. All right, let's just look at these pictures. These are so this is the modern spring. This is the ancient spring. You can see that these features, these cyanobacteria, are diffuse. They're recrystallizing over time. One interesting thing is that there's ferrihydrite. Somebody yesterday talked about unusual minerals and things that are thermodynamically unstable, and why are they present? So why is ferrihydrite present in a 100,000-year-old microbial mat? Probably ferrihydrite's a mineral that recrystallizes to more stable phases within weeks in a laboratory. So the fact that it's there is very unusual. The fact that it's there and it's that old is very unusual. All right, these are these bugs. We're going to just skip that. And so here are the brushy basin, or I'm sorry, this is the modern spring and this is the brushy basin member. And we see some similar features, these branching filaments, framboids and spheroids, which are, have been in the literature, have been noted to be possible biosignatures. These are associated with these tests of diatoms, and there's diatoms present in both of them. Okay, I'm going to skip over that. All right, so to go to just the biogenicity, these are, so what I did was I dissolved these in hydrofluoric acid and found algal fossils in the vugs. All right, we're going to skip this. Whoops. All right, well, we'll go here. So anyway, bottom line is I did look at, I looked at all of these features, and they're segmented stalks, and those are probable fossils according to these criteria. Those branching filaments are possible fossils. The tests, oh, this got messed up here. Probable fossils. That spheroidal, those spheres, those iron oxide spheres are probable fossils. And anyway, so the conclusions are that these microbial fossils are associated with these macroscopic trace fossils, these charophyte molds. And so that's really the point I wanted to make here, is that I think that those rocks on Mars bear further investigation. And there's my daughters again, and there's some funding and people who helped me.
Thank you, Sally. We have about 1 minute and 30 seconds for questions.
Oh, darn, I could have gone.
Anyone? Okay, thank you, Sally.
Yeah.